Well, hi guys. Today we're going to have a look at solving quadratic equations by inspecting graphs of quadratic equations, and they are very exciting and easy to do. So let's have a look. Now, guys, if we make a graph of a quadratic equation, that is y equals ax squared plus bx plus c, and we make that into a graph, okay, whatever a, b and c might be in a particular instance, then we'll get a shape called a parabola, and that is a superstar in the world of maths, that little shape. So there's one, and that's just, I've just drawn that in general terms. Y equals ax squared plus bx plus c. It's a particular one, but let's not bother what particular example that I've used there. That is the general shape of a parabola, okay? So we can solve a quadratic equation, ax squared plus bx plus c equals 0, graphically. Yes, you can. So if y equals ax squared plus bx plus c on the graph, and we're trying to solve for ax squared plus bx plus c equals 0, which after all is what y is on the graph, you see. So therefore we're trying to look for when this thing, ax squared plus bx plus c, or y, equals 0. And you know on this graph where y equals 0. Have a look. Okay, up here y is positive, that's above the x-axis. Down here y is negative, below the x-axis, but anywhere on the x-axis y is 0. Y is 0 right along here, right? That's the thing. So we just look for where the graph is 0. That means anywhere along the x-axis where y is 0. Okay, so hence the solution to ax squared plus bx plus c equals 0 on a graph of y equals ax squared plus bx plus c is where the graph intersects the x-axis, or where y is equal to 0. Okay, thus for solutions to y equals ax squared plus bx plus c equals 0, we just read the solutions for x off directly as the x-intercepts here and here on the graph. That's the line there, that green line there is a graph of y equals 0 because it's the x-axis, okay? So obviously the graph is 0 here. The value of ax squared plus bx plus c is 0 here, and the value of ax squared plus bx plus c is 0 here. So they are the solutions. Yes, isn't that marvellous? So what an easy way to do it. So the x-intercepts are the values of x for which y equals 0. They are the solutions to ax squared plus bx plus c equals 0, and that fills us with great hope and aspiration. Right, example 1, guys, let's go for this. Find the solution, otherwise known as the roots, that's just another name for the solutions for x, of each of the following quadratic equations by inspecting their corresponding graphs. Round the answers off to one decimal place where appropriate. Alright, no problem. They are the two equations we've got to solve. X squared plus x minus 12 equals 0, and 2x squared minus 4x minus 7 equals 0. Let's go with A today. Now I just drew that for you on my trusty little computer thingy, and that's it. Now, yes, you just look, you hone in here. Look, this is here. That's where the value of y equals 0. This is the value of here, y equals 0. So you can just read them off. That's 1, 2, 3. So x is 3, where y is 0 there, and x is minus 1, minus 2, minus 3, minus 4, where y is 0 there. Okay, so there's my green line, y equals 0, there are my values, and therefore they are the solutions. The parabola crosses the x-axis where y equals 0, at x is minus 4 and x is 3. Hence the solutions to x squared plus x minus 12 equals 0 are x equals minus 4 or x equals plus 3. It's very easy, isn't it, guys? Now this next one is not a it's not a whole number solution one. It sort of crosses in funny spots. You see that? Look, it's not exactly on the x is 3, and it's not exactly on the x equals minus 1 over here. But no matter, it doesn't matter. There's my line y equals 0. There are my x-intercepts, but they're not whole numbers. So from the graph we can see that the x-intercepts are not whole numbers, but we can estimate them from the graph. That's all you can do from the graph if they're not crossing on exactly whole number spots. So we can estimate them as x is minus 1.1 or thereabouts. Just, it's a bit rough, but, it's good enough for the purposes of what we're doing. Or x is plus 3.1. Do you get that? Very excellent. Now, NB, guys, if we solve the equation 2x squared minus 4x minus 7 equals 0, by completing the square, as we've been doing ad nauseam in previous videos, and factorising as a difference of two squares, and then using the null factor law, we would have found out, and it would be a great exercise for you to do, if you feel like it, solving this thing in the way that I've just described. We would find that the solutions from the null factor law are x is 2 minus 3 root 2 all over 2, and x is 2 plus 3 root 2 all over 2. And if you decimalize those, you'd get exactly what we got, guys. Yeah, so it all ties together, it all hangs together, it's all mighty fine. Now, some equations, some quadratic equations have two solutions, e.g. this one. Yes, that's another way of writing that after I've factorised it into linear factors. And that means x would be minus 3 or x would be plus 2. And here they are. X is plus 2, x is minus 3. That's all pretty straightforward, isn't it, guys? Yes? Okay. Now, there they are. Now, the shocking news is that some quadratic equations have only one solution. You kind of wish they'd make up their mind, don't you? But some have two, some have one, and actually some have none. So we're just going through that now. This is an example of a one-solution quadratic equation. It's actually a perfect square. Yes, it's x plus 2 all squared, and there it is. Now, see, look, there's the one solution, you see? Just one. Because it doesn't, the quadratic doesn't dip under the x-axis. It just kind of comes in like an asteroid and goes and just sort of touches it and then runs away again. Okay, so the solution there would be x is minus 2, wouldn't it? Yes, great. So that's that one. All right. Now, yes, some quadratic equations have no solutions at all. That's pretty amazing. So can you imagine the shape or where the quadratic might be on the Cartesian xy plane there for it to have no solutions? Can you imagine? Well, here's an example of one which has none. Okay, x squared minus 4x plus 6, which is this one here after I complete the square. But you'll notice, guys, there's no minus here, so I can't turn this into a difference of two squares because that's a plus. That is the telltale sign of quadratics which do not have solutions. Yes, in terms of x points where they cross the x-axis. See, look, this one's wholly above the x-axis. Or if you had another one wholly below the x-axis. They don't cross the x-axis or touch the x-axis, therefore there's no solutions. Okay? Yes, there it is. Does not touch the x-axis, therefore there's no solutions to that equation. Good heavens above, wonders will never cease. Now, this is an interesting little section here. It's called confirming that solutions are correct. It's pretty easy to do, guys. You should always check that your solutions are correct for any equation at all by substituting them back into the original equation, not just quadratics, but any equation, and then checking that the equation works, because we all make mistakes, we all get tired, we all get a little bit out of it, our brains don't work properly, so you always check that by substituting your solution back into the original equation, that the left-hand side in fact does equal the right-hand side, e.g. the equation works. Okay? Have a look at this. Verify that the solutions to the following quadratic equations are as specified. So we give you the solutions now. You've got to just check that they are right. Okay? So we're saying, here's your quadratic equation. Here are the solutions. You better check whether they're right. Okay? Now, another example there. All right? So let's go for it. What about A? So the left-hand side, guys, is x squared plus x minus 6, right? Now, we're going to substitute. We're going to substitute x is minus 3, the first solution, into that left-hand side, and if that solution is correct, we should get 0, which would be the right-hand side. In other words, the left-hand side equals the right-hand side, so therefore this is a valid solution. So let's put it in. We've got minus 3 squared for the x squared term, plus negative 3 for the x term, minus 6. Now that should come to 0, which it looks like it's going to, and everything's great. Yes, it is. So therefore that's equal to the right-hand side. So if x is minus 3, then the left-hand side equals the right-hand side, and everything's good. Therefore x is minus 3 is a valid solution. You should always do that. Whenever you solve any equation, you should always plug it back in and make sure it works. Okay, substituting, x is plus 2. Let's go for that. So the left-hand side in that case would be plus 2 squared plus 2 minus 6, which is going to be 4 plus 2 minus 6, which is 6 minus 6, which is 0, and everything's beautiful. That is the right-hand side, and therefore that is also a valid solution as required. Okay, that's all you have to do, guys. Let's do B now. We've only got one solution there, so that's easy. The left-hand side of the equation is x squared plus 4x plus 4. We're going to substitute x is minus 2 into that, and we get minus 2 all squared plus 4 times minus 2 plus 4. Now, that comes to 4 minus 8 plus 4, which it is 0. Yes, it is. It's marvellous. So therefore, x equals minus 2 is a solution of that equation as required, because the left-hand side equals the right-hand side when you plug that value of x in. So that's what we're doing there. Now, one final example to finish off, and then we'll all get out of here. We've got a golf ball. The golf ball is hit at the start of the fairway. Its trajectory is that. My goodness. That is the trajectory of that's the y is the height, and the x is the horizontal distance from where it was hit along. That's the horizontal distance along the ground. The y is how high it is up in the air. Okay, and they're both measured in meters. All right. So what we've got to do is use the graph to find, first of all, the maximum height reached by the ball, and secondly, how far the ball landed away from the golfer who hit the ball. Well, we'll get a graph first. Lovely looking graph. Now let's just feast our eyes upon this and work it all out. This is y, so this is the height. This is x, so this is the horizontal distance along the grass, okay, from where he hit the ball, or she hit the ball. Now, this point here is the origin, 0 and 0. This point here is x is 200 and y is 0. This point here, it looks like the middle of the symmetrical parabola, because they're always symmetrical, parabolas are. And the point of symmetry is always the highest or lowest point, whichever it may be, based on the shape of the parabola. Therefore, okay, that's 100 and that's 40 high. All right, so I think this is very easy. Number A today. From the graph, guys, the maximum height occurs when x is 100. Yes, it's the top or the vertex of the parabola. So so that is 40 meters up in the air. My goodness, that went pretty high. And also B, what is that? How far the ball landed away from the golfer who hit it. Well, that's pretty easy. Look, when y is 0, that is when it's on the ground, isn't it? So x is 0 here, or x is 200 here. So I would say that ball landed 200 meters from the golfer, and I'd also say that you're a star, and you'll go far. Huzzah! So that was a nice, easy little session, wasn't it? It makes light work of quadratics when you can just look at a graph of a quadratic and then look where it equals 0, which happens to be the x values of the solutions of ax squared plus bx plus c equals 0. Alright, have a wonderful day and we'll see you next time, and all the best to you.